Fact 1. A black hole is a region of space where gravity is so strong that even light cannot cross its boundary. This boundary is called the event horizon. Anything that falls inside loses its causal connection to the outside world. The radius does not depend on density but only on mass and is described by the Schwarzschild formula, R equals 2gm by c squared. For the Sun, a hypothetical horizon would be about 3 kilometers, and for Earth, approximately 9 millimeters. It is important that black holes do not vacuum space. An object in a safe orbit will rotate stably, as it would around any mass. Near the horizon, time flows more slowly, gravitational time dilation, and light experiences a significant redshift. A distant observer will never see a body cross the horizon. Its image will freeze and fade to invisibility. Fact 2. The most reliable way for a black hole to form is the collapse of the core of a very massive star after its thermonuclear fuel is depleted. When the pressure from degenerate gas and neutrons can no longer support the weight of the outer layers, gravity takes over. Depending on the star's mass and composition, this results in a supernova or a silent, direct collapse into a black hole. The threshold masses depend on metallicity and mass loss due to stellar wind. Estimates suggest tens of solar masses for the initial star and approximately 2 to 3 solar masses for the remaining core. In binary systems, fallback is possible, where some ejected material returns, increasing the mass of the newly formed hole. Such an evolutionary path explains the existence of many X-ray binary systems. Fact 3. Supermassive black holes, ranging from millions to tens of billions of solar masses, are located at the centers of most large galaxies. In the Milky Way, the central object, Sagittarius A star, weighs about 4 million solar masses. Its presence is confirmed by the orbits of stars, which over years of observation trace elongated ellipses around an invisible center. In galaxy M87, the supermassive black hole has a mass of approximately 6.5 billion solar masses and fuels a giant jet. The Event Horizon Telescope captured the first image of such a black hole's shadow, a dark spot against a luminous accretion flow, which served as direct confirmation of the general relativistic picture. These observations capture not a hole in the picture, but a gravitational shadow, a region from which light is least likely to escape to us. Fourth fact. According to quantum field theory, black holes emit radiation on a curved background, known as Hawking radiation. An external observer sees it as if the hole has a temperature inversely proportional to its mass. Smaller ones are hotter, larger ones are almost cold. For a stellar mass object, the temperature is microscopic, far below the cosmic microwave background, making such radiation currently undetectable. Theoretically, a black hole should evaporate, losing mass, with its lifetime growing as the cube of its mass. Supermassive ones will live much longer than the current age of the universe. The mechanism itself relies on quantum fluctuations occurring at the event horizon. But the details of the information paradox, how to reconcile quantum unitarity and evaporation, remain a subject of active research and debate. Fifth fact. Matter falling towards a black hole forms a hot accretion disk. Friction and magnetic fields heat the gas to millions of degrees, causing it to shine in X-rays and ultraviolet light. The efficiency of converting mass into energy in such a gravitational power plant is enormous. For a rapidly rotating Kerr black hole, it can reach tens of %, surpassing nuclear fusion. Streams of plasma shoot out along the axis of rotation at speeds close to the speed of light, forming jets. One mechanism involves extracting rotational energy through magnetic fields stretched by the ergosphere. Luminosity is limited by radiation pressure, the famous Eddington limit. An overly bright disk will start to inflate and push out gas, stabilizing the feeding rate of the central monster. Fact 6. A rotating black hole, the Kerr solution, possesses a special region outside the event horizon called the ergosphere. Within the ergosphere, space-time is dragged by the rotation, forcing even light to move with the general vortex rather than remaining stationary relative to distant stars. This is not the horizon. Escape is still possible, but every world line must rotate in the direction of the spin. The Penrose process is based on this characteristic. A particle decays in the ergosphere, one component falls beyond the horizon with negative energy for an observer at infinity, and the other flies away, carrying more energy than the original particle had. In the limit, colossal resources can be extracted from rotation, theoretically up to about 29% of the mass energy of an extreme black hole, making the ergosphere a natural cosmic flywheel, albeit extremely difficult to access. Fact 7. The radius of the innermost stable circular orbit, ISCO, defines the inner boundary for safe rotations within the disk. For a non-rotating Schwarzschild black hole, ISCO is located at 6 gm/c², which is 3 Schwarzschild radii. In contrast, for a maximally rotating Kerr black hole with prograde motion, ISCO shifts to almost the event horizon itself. This alters the thermodynamics of accretion. The conversion rate of mass into radiation increases from approximately 5 to 6% for a Schwarzschild black hole to a theoretical near 40% for an extremely fast-rotating one. Astronomers estimate spins by analyzing X-ray spectra. Reflection from the inner disk and continuum fitting allow them to conclude that some black holes in binary systems and galactic centers rotate with a spin parameter A* close to unity, which aligns with the high efficiency and luminosity of their accretion engines. Fact number 8. Around a black hole, there is a photon sphere, an orbit at a distance of 3 gm/c² for the Schwarzschild case, where light can circle, but any slight deviation will lead to escape or fall. The strong curvature creates what an observer sees, a gravitational shadow. Its diameter for a non-rotating hole is about 5.2 Schwarzschild radii, and for a rotating one, it is slightly distorted and shifted. In reality, the shadow is framed by a bright photon ring, rays that have orbited the object multiple times. Doppler boosting makes one side brighter, where gas in the disk rushes towards us. It is this contrast that the Event Horizon Telescope interferometers captured. Not a hole in the light, but a region from which rays hardly reach us, having become entangled in the extreme space-time geometry and swallowed by the horizon. Fact 9. Spaghettification is not a metaphor, but a consequence of tidal forces. The difference in gravitational pull between your head and feet stretches and compresses your body. For stellar mass black holes, this difference is so great that it's deadly long before the event horizon. However, with supermassive black holes, the field gradient at the horizon is gentler. An astronaut, disregarding radiation and magnetic cataclysms, could cross the boundary without noticing immediate disaster. The fatal end would occur deeper at the singularity. When an entire star approaches the central hole, the result can be tidal disruption. The star is torn apart, half its material flies away, and half returns, causing an ultraviolet X-ray flare and a characteristic luminosity drop of approximately T to the -5/3. Such events, tidal disruptions, have been recorded many times and serve as beacons for hidden monsters. 10th fact. The mergers of black holes cause ripples in the fabric of spacetime, generating gravitational waves. These are tiny stretches and squeezes, fractions of a proton over kilometers. In 2015, the first signal from a pair of black holes, GW1509, was detected. It featured a characteristic chirp that increased in frequency and amplitude until objects with masses around several tens of suns merged into one, releasing energy equivalent to 3 solar masses in pure form within fractions of a second. Detectors LIGO and Virgo have since collected dozens of similar events, and their statistics reveal a diversity of masses and spins. These observations not only confirm general relativity and strong fields, but also shed light on how these pairs originate. Either they were born as close binary stars, or they found each other later in dense clusters where gravitational encounters bring strangers together. Fact 11. The history of black holes began long before the term itself existed. In 1916, Carl Schwarzschild found the first exact solution to Einstein's equations for a spherically symmetric mass. In 1939, Oppenheimer and Snyder showed that a sufficiently massive stellar core must inevitably collapse. The Chandrasekhar limit, around 1.4 solar masses, separated the fates of white dwarfs and supernovae, while the subsequent Oppenheimer-Volkoff limit, around 2 to 3 solar masses, distinguished neutron stars and black holes. The term black hole itself was popularized by John Wheeler in the late 1960s, although it had appeared in the press earlier. Since then, the idea has moved out of theoretical obscurity. In the 1970s, Bekenstein linked the area of the event horizon to entropy, and Hawking predicted quantum evaporation, transforming black holes from cold graves into thermodynamic objects. Gradually, the conceptual map was enriched with the ergosphere, shadow, radiation, and gravitational waves, and the hypothesis became an observable reality. Fact 12. Hunting for black holes involves a set of clever indirect methods. In X-ray binary systems like Cygnus X1, the invisible companion sucks gas from a neighboring star. The hot accretion flow emits in the hard spectrum, and by observing the movements of the bright donor, astronomers determine the dynamic mass of the unseen object. If this mass exceeds the stable limits for a neutron star, it's a strong candidate for a black hole. In galactic cores, masses are estimated from the speeds of stars and gas and through reverberation, the delayed response of broad emission lines to disk flares. The gravity interferometer tracked the star S2 on its ellipse around the Milky Way center and recorded gravitational redshift at pericenter, confirming a supermassive object. The Event Horizon Telescope project linked radio telescopes worldwide to see the shadow, first M87 star, then Sagittarius A star, visual signatures of extreme gravity, not just holes in light. Fact 13. A persistent myth is that a black hole sucks in everything around it, destroying galaxies. In reality, its gravity follows the same laws. At distant orbits, it behaves like ordinary mass, and planets or stars can orbit stably if they do not cross the region where stability is lost. Another popular fear concerns many holes from colliders. However, cosmic rays with energies higher than those in accelerators have been bombarding Earth and stars for billions of years. If such microscopic objects were born and survived, we would see their effects. Furthermore, according to theory, the hypothesized tiny holes evaporate through Hawking radiation extremely quickly. The myth that everything will eventually fall into a hole is also incorrect. The evolution of the universe includes expansion. The decay of baryons is questionable. And there is the thermodynamics of dark energy. There are many scenarios, and an all-consuming finale is neither the only one nor proven. Fact 14. Black hole records impress with scale and speed. Supermassive black holes in early universe, quasars, just a few 100 million years after the Big Bang, were already accumulating masses of hundreds of millions and more. This creates a mystery of how they managed, with discussions revolving around seeds from direct collapse of gas clouds, rapid growth during super Eddington accretion episodes, and frequent mergers. For the giant M87 star, the Schwarzschild radius is tens of astronomical units, which in the solar system scale is the size of Pluto's orbit. Yet all its mass is packed into a region from which no light escapes. At the other end of the scale are light stellar mass holes. In binary systems, they are estimated at several to tens of solar masses, and the spins of some, based on spectral and relativistic signs, are close to their limits. Even quiet supermassive ones, like our SGR-A star, occasionally cough with flares when a random portion of gas falls into their maw. 15th fact. The aesthetic of the gravitational abyss was quickly adopted by culture. In Interstellar, the visualization of a black hole was created based on calculations led by Kip Thorne. Rays were traced in curved spacetime, allowing the disk to be seen not only in its plane, but also from above, as light bends around the hole, forming an aura. The film slightly simplified brightness asymmetries and colors so the viewer could distinguish details, but the concept of a photon ring and Doppler boosting from approaching gas reflects real physics. The scale of time dilation on a planet near the event horizon remains debatable in the film. For years to pass in an hour, parameters would need to be extreme and difficult to reconcile with a stable orbit and tidal survivability. Nevertheless, the movie achieved something rare. It brought rigorous mathematics into mainstream cinema and provided the audience with an image close to what interferometers depict today. Fact 16. The relativistic dragging of spacetime by rotation, known as the lens-Thirring effect, causes the orbits of particles and gas clumps to precess around a black hole's axis. Closer to the horizon, this leads to the Bardeen-Pedersen effect. Inner disk layers align with the spin's equatorial plane, while outer layers remain tilted, creating a warped flow geometry. Such bending alters jet direction and can explain smooth jet turns on scales from astronomical units to parsecs. In X-ray systems, precession manifests as quasi-periodic oscillations, weak but stable brightness beats on millisecond-to-second timescales. Their frequencies, dependent on mass and spin, serve as indirect clocks for strong gravity. By comparing several oscillation modes, researchers attempt to reconstruct the near-horizon's geometry without direct imaging. Fact 17. Black holes not only consume, but also shape their surroundings through feedback. The energy from accretion and jets heats and expels gas, slowing down star formation in galactic cores. Cavitation bubbles, inflated by active galactic nuclei jets and illuminated by the X-ray glow of surrounding plasma, are visible as voids in the hot gas of clusters. This counteraction to gravitational cooling helps explain why massive elliptical galaxies are often red and dead rather than actively forming stars. The masses of central black holes correlate with bulge properties such as stellar velocity dispersion and luminosity, indicating co-evolution. When a nucleus becomes active, we observe a quasar, a superluminous object with high accretion, broad and narrow lines, and variability on timescales of days to years. As fuel runs out, the nucleus shuts down, but traces of past outbursts like shock fronts and chemical enrichment remain detectable in the interstellar medium for a long time. 18th fact. Black holes possess thermodynamics. The classical laws of black hole mechanics formally resemble ordinary ones. Surface gravity acts as temperature, the area of the event horizon corresponds to entropy, and mass represents internal energy. Bekenstein was the first to suggest that entropy is proportional to area, and Hawking calculated the coefficient. For every quarter of the area in Planck units, there is 1 bit of disorder. This leads to a striking conclusion. A black hole is the most capacitive information carrier per unit volume. However, how this information disappears or is preserved during evaporation remains an open question, known as the information paradox. Models propose soft hair, gravitational replication effects, holography, and firewalls, but there is no consensus. It is honestly noted that this is an active area of theory where rigorous mathematical results and observable consequences are still rare and require careful interpretation. 19th fact. Accretion can vary. The classic Shakura-Sunyaev thin disk is cold, geometrically thin, and radiatively efficient. Almost all gravitational energy is converted into light. However, at low inflow rates, a rarefied hot flow forms, which is radiatively inefficient, RIAF/ADAF. In this flow, energy is carried inward and the spectrum shifts towards hard X-rays. In X-ray binaries, these modes alternate. The soft state is dominated by thermal disk radiation, while the hard state is dominated by a hot electron corona that Compton scatters soft photons. Transitions are accompanied by the activation or weakening of compact jets, indicating a link between the disk, corona, and outflows. A fundamental plane of activity has been observed. The mass, X-ray, and radioluminosity of objects, from stellar to supermassive, fit a single scaling law, emphasizing the universality of accretion physics. Fact 20. Primordial black holes are hypothetical objects that are thought to have formed not from stars, but from high-density fluctuations in the early universe. Their masses could have ranged from asteroid-sized to stellar mass and beyond. In recent years, it has been discussed whether such objects could constitute a significant fraction of dark matter or explain some sources of gravitational waves. However, constraints are strict. Stellar microlensing, gamma-ray background from the evaporation of small black holes, dynamics of star clusters, and cosmological data narrow down the allowed mass windows. Observational evidence has not yet provided a definitive answer, and the scenario remains debated. It is possible that some LIGO/Virgo events are linked to primordial holes, while others are entirely from the stellar channel. It is accurate to say that this is a beautiful idea at the intersection of cosmology and astrophysics that still awaits decisive tests. Fact 21. Gravitational lensing is a subtle signature of a black hole, where its field bends the light from a distant star or galaxy. Strong lensing can create an Einstein ring or split the source into arcs. But for single stellar mass objects, more modest effects are usually seen. A temporary brightening, microlensing, and a tiny shift in the visible position of the background object, an astrometric trace in billionths of an arcsecond. This is precisely how telescopes like Hubble and Gaia have reported candidates for lone black holes in recent years. The light from distant stars behaved for days and months as if it were being pulled by an invisible mass of several solar masses. The method is valuable because it doesn't require accretion or X-rays. It allows us to observe dim objects that would otherwise remain completely hidden, offering a rare opportunity to measure the mass of the galaxy's silent gravitational skeletons. Fact 22. The no-hair theorem states that a stationary, isolated black hole in general relativity is completely described by three parameters: mass, spin, and electric charge. In real astrophysics, the charge is rapidly neutralized by surrounding plasma, leaving only mass and spin. This leads to strict predictability after a merger. The new hole should ring with a set of quasi-normal modes like a space-time bell chime with precisely calculable frequencies and damping. Gravitational wave detectors aim to capture these overtones to perform black hole spectroscopy and test Kerr geometry. Will the observed notes match the strict predictions? While errors are currently large, the first hints align with the theory. Any stable deviations would be a sensation, indicating either that hair truly exists at the horizon or that new physics beyond general relativity is needed. Fact 23. Magnetic fields are the hidden reinforcement of accretion machines. Through the polarization of light, measured by event horizon interferometers, ordered structures have been detected near the shadow of M87. These fields are twisted like hoops and spokes, directing plasma towards the poles. In such an environment, the magnetically arrested disk (AAD) regime is possible. Here, the incoming flow brings so much magnetic flux that it pushes back against the black hole, slowing further infall while simultaneously feeding the jet. The Blandford's-Nyack mechanism extracts the black hole's rotational energy through these fields, acting like a cosmic-scale electromagnetic generator. Observed correlations between radioluminosity, polarization, and jet power support this picture. A richer magnetic reservoir and higher spin lead to a more stable and brighter jet, capable of piercing the interstellar medium for thousands of light-years. Fact 24th. Intermediate mass black holes are the missing link between stellar and supermassive black holes, with masses ranging from hundreds to hundreds of thousands of solar masses. Their existence is logical for scenarios of galactic monster growth, but observations are few and ambiguous. Candidates flare up as ultraluminous X-ray sources in the peripheries of galaxies, where classical accretion struggles to achieve such luminosity without extra masses. There are also dynamic hints in dense globular clusters. Stars move as if an invisible heavy mass sits at the center. Gravitational wave events with product masses around 100 solar masses also push towards the idea of hierarchical mergers, when holes are born, merge, and pair up again. For now, it's a mosaic of indirect arguments, but if intermediate mass black holes are confirmed, they will become the natural seeds for early quasars. Fact 25th. According to current data, the universe contains a background of nanohertz gravitational waves. This is an ultra-low frequency hum, which, according to interpretations, is created by a population of supermassive black hole binaries in merging galaxies. These low frequencies cannot be detected by laser interferometers. Instead, millisecond pulsars, which are extremely precise beacons, serve as clocks. If the fabric of space-time experiences slight undulations, the arrival times of the pulses drift synchronously across the sky. International pulsar timing projects have reported statistical evidence of such a background. The signal exhibits the required angular correlation and spectrum consistent with expectations from a large population of galactic nuclei at various stages of spiral convergence. This is not a single loud event like those detected by LIGO, but rather the combined faint rustling of a billion distant dances, offering clues to the history of galaxy growth and their massive black hearts. Fact 26th. When two black holes merge, gravitational waves carry away not only energy but also momentum. If, due to masses or spin orientations, the radiation is somewhat askew, the new hole receives a push, a gravitational kick. Calculations and modeling suggest this kick can reach thousands of kilometers per second, though hundreds are more commonly discussed. For supermassive black holes at galactic centers, this is dramatic. Such speeds are comparable to gravitational confinement, and the object can shift from the core or even fly out into the halo. Astronomers search for shifted active nuclei, asymmetric emission lines, and quasars with visible displacement relative to the stellar center, potential traces of kicks. The stage before the impact itself leaves other marks. A binary hole ejects stars, creating shattered nuclei. And after the kick, it may carry away a compact star cluster, a hypercompact cluster gravitationally bound to the runaway. Fact 27th. The diet of a black hole in a quiet galaxy consists of rare tidal stellar disruptions. It is estimated that in a typical galaxy, such an event occurs approximately once every 10,000 to 100,000 years. A star gets too close, is torn apart by tides. Some of its matter flies away, and some falls back, producing a flare with a characteristic luminosity decay as T to the -5/3. There are jetted cases, where a narrow jet is activated and the signal breaks through into the gamma and X-ray range. There are optically thick cases, where the lion's share of energy is processed by winds and radiated in ultraviolet and optical wavelengths. An infrared echo flare from heated dust torus around the core is often visible. There are also partial disruptions. The star is bitten into, and it returns to an elongated orbit, giving periodic bursts. These diverse modes help to indirectly measure the masses and spins of hidden monsters, as well as to study how gas circulates and loses energy near the horizon. Fact 28th. One reliable spinometer is the relativistically distorted iron K-alpha line. In a calm atom, it lies at about 6.4 keV. However, in the near-horizon disk, light experiences gravitational redshift, Doppler broadening, and aberration. The result is an asymmetric sawtooth with a smeared red wing extending up to several keV. Modern X-ray observatories simultaneously measure this line and the reflection hump at 20 to 30 keV, as well as capture the delays between changes in the corona and the disk's response, reverberation on millisecond to hour timescales. By comparing the line shape, delays, and continuum, they model the position of the inner disk edge linked to ISCO and derive the spin. The method is strong in statistics, but vulnerable to systematics, corona geometry, disk ionization, and absorption along the beam. Therefore, spin estimates are checked with several independent approaches, achieving agreement before drawing conclusions about the speed of a specific hole. Fact 29th. To grow a supermassive black hole, a galaxy must deliver a lot of cold gas to its center and strip away its angular momentum. This is achieved through galaxy mergers, bar-and-bar phenomena, spiral instabilities, and turbulent inflows from the intergalactic medium. In the core, the gas becomes denser, forming stars and simultaneously feeding the disk. Some light from the core is shielded by dense dust and gas, creating a torus. When viewed along the torus's plane, we see type 2 narrow lines, and when viewed from above, we see type 1 broad lines. This unification picture is complicated by evolution. Many nuclei are so densely hidden, Compton thick, that their contribution is only apparent in hard X-rays and the cosmic X-ray background, the peak of which is explained by the sum of many hidden AGNs. Activity occurs in bursts, a duty cycle. Short, by cosmic standards, outbursts lasting hundreds of thousands to millions of years, with pauses during which the nucleus goes dark. Fact 30. The near future of research is multi-channel strong gravity astronomy. A next-generation radio interferometer aims not only to photograph shadows, but also to capture movies around Sagittarius A star, tracking plasma blobs orbiting in minutes and hours. Optical giants with adaptive optics will continue to track streamer stars near the galactic center, refining the gravitational potential. X-ray spectrometers with microcalorimeters provide razor-sharp lines and reverberation maps, allowing measurement of corona height and wind dynamics. A space-based gravitational wave antenna, sensitive in the millihertz range, targets intermediate and supermassive black hole pairs, promising tomography of the merger universe. Wide-field optical and infrared sky surveys will catch thousands of tidal disruptions, turning rare curiosities into statistics, and making horizon physics a realm of precise, repeatable measurements. Fact 31. In the vicinity of Sagittarius A star, between 2011 and 2014, a mysterious object designated G2 acted as bait. This object was a compact cloud of dust and gas that traversed its aphelion on an elongated orbit, passing the pericenter at a distance of approximately thousands of Schwarzschild radii. Astronomers anticipated a spectacular event. It was expected that a portion of the material would be torn away, heated by tidal forces, and flare up in X-ray and radio wavelengths, akin to a mini-feast in honor of the black hole. However, the observed outburst was modest, as if the cloud maintained its shape better than a gas droplet. This led to an alternative hypothesis. G2 was not pure gas, but rather a young star or a recently merged pair, enshrouded in a dusty envelope that survived the close encounter. Subsequent observations revealed that even in the starving center of the galaxy, matter supply occurs in portions, and not every close passage results in a grand celebration, with the dynamics of the regions near the horizon proving more complex than straightforward models. Fact 32nd. EMRI, or extreme mass ratio in spirals, are systems where a stellar mass object spirals towards a supermassive black hole for years. Their gravitational waves lie in the millihertz range and carry a detailed map of Kerr geometry, hundreds of thousands of orbits, precessions, and resonances. It is estimated that the next-generation space antenna will be able to detect such signals from distant galaxies, allowing for tests of black hole hairlessness. The slightest deviations in frequencies and phases will reveal discrepancies from the ideal metric. EMRI are born when, in a stellar cocktail around the core, an object loses energy in gravitational encounters and falls towards the center. Their signals are long-lived and provide precise masses and spins of central black holes, as well as insights into the structure of dense nuclear clusters, where massive stars, black holes, and exotic gravitational dances reign. Fact 33. Microquasars, which are nearby binary systems featuring a black hole, exhibit superluminal jets, even though light does not violate Einstein's limit. The key is geometry. Plasma travels at nearly the speed of light at a small angle to the line of sight, and due to projection, the apparent transverse velocity exceeds c. Classic examples include sources like GRS 1915 + 105 and GRO J16 55-40. In these systems, the luminosity and spectrum of the disk, the X-ray corona, and the radio jet change in coordination, much like scenes from a single play. In a flaring state, the disk increases its thermal contribution, the corona weakens, and the jet can detach and travel as plasma knots. In the hard state, conversely, the jet is stable and the X-ray emission is harder. These connections form a cosmic laboratory for studying the disk-corona-jet relationship, scalable across many orders of mass. The same laws governing microquasars also successfully describe the behavior of active galactic nuclei. Fact 34. Besides narrow jets, black holes also emit powerful winds. In the spectra of active galactic nuclei and X-ray binaries, blue shifted lines of highly ionized iron are visible, indicating ultra-fast outflows with speeds up to tens of % of the speed of light. There are also warm absorbers and broad absorption lines in the ultraviolet, known as BAL quasars, where winds carry away colossal momentum. These outflows are likely driven by a combination of radiation pressure and magnocentrifugal forces. They compete with accretion, transport energy to the nuclear scale and beyond into the interstellar medium. Observations of delays and polarization suggest a complex geometry, including equatorial and polar components, variable funnels, and a dust screen. The outcome is important for galaxy evolution. Winds and jets together regulate the thermostat, preventing gas from cooling uncontrollably and forming stars. 35th fact. To understand how a disk and jet behave near the event horizon, physicists construct GR-MHD simulations. This involves solving magnetohydrodynamic equations in curved spacetime, incorporating general relativity. The output reveals turbulent eddies, magnetic loops, and hot spots that transfer angular momentum outward and energy into the corona and jets. Next, radiation transfer is included. Rays are traced along geodesics, accounting for redshift, Doppler effects, and gravitational focusing. This process yields synthetic images and light curves comparable to radio interferometry and X-ray data. This is how ideas about magnetically arrested disks, corona height, and field structure near M87 star and SGR-A star are tested. The convergence of models and observations is not merely a visually appealing outcome. It's a verification that the initialization equations, plasma microphysics, and chosen metric accurately describe real-life phenomena at the point of no return. Fact 36. The masses of black holes originating from stars are not distributed continuously. Theorists have long predicted a pair instability gap. In the cores of massive stars, at temperatures around 1 billion Kelvin, gamma rays produce electron-positron pairs. This causes a drop in pressure, leading to the core's collapse and explosion. If the helium core's mass is sufficiently large, a star can undergo a series of pulsations, shedding its outer layers, pulsational pair instability, leaving behind a relatively light black hole. With even greater masses, complete pair instability occurs, destroying the star entirely without residue. In this mass range for black holes born from single stars, a void was expected. Gravitational wave observations have added intrigue. Systems with components seemingly from the forbidden zone are occasionally detected, suggesting hierarchical mergers or specific low metallicity conditions. The outcome? The mass distribution chronicles the evolution of stars and their unions within dense clusters. Fact 37th. Our galaxy is believed to harbor millions of stellar mass black holes, either within binary systems or as solitary wanderers. While exact estimates vary, the numbers are in the tens of millions spread across the galactic disk and bulge. We only see the tip of the iceberg, a few tens to hundreds of X-ray binaries where accretion reveals the invisible object. The rest remains silent. They are detected through microlensing, the temporary brightening of a distant star when an unseen mass passes along the line of sight. During such events, the characteristic duration can range from weeks to months. In rare instances, a tiny astrometric shift in the star's position can be observed, allowing the mass of the lensing object to be reconstructed. This reveals a dark object of solar masses without its own luminosity. Large surveys and precise astronomy are gradually uncovering a catalog of these quiet gravitational phantoms, enabling estimates of their numbers, velocity distributions, and even insights into the kicks they received during their birth in supernovae. Fact 38. Superradiance is an exotic method for extracting energy from a rotating black hole. A classic example is the Zeldovich relativistic effect. A wave reflecting off a rotating absorber can gain energy from its spin. Direct implementation of this in astrophysics is challenging. However, if light bosons, such as axion-like particles, exist, they can form atom-like energy levels near a black hole. Through superradiance, these levels become populated, similar to a laser medium. The outcome is an expanded cloudy configuration that siphons angular momentum from the black hole, slowing its rotation, and can emit narrowband gravitational waves for years. By examining the spin distribution of stellar and supermassive black holes, constraints are already being placed on the possible masses of such particles. If their masses fell within certain ranges, there would be fewer rapidly spinning black holes. This illustrates how event horizons transform into laboratories for physics beyond the standard model. Fact 39th. Visibly changing active nuclei are a phenomenon where a quasar loses or gains broad lines in its spectrum over years and drastically alters its luminosity. The classic unification scheme explained differences by viewing angle, but here the object itself changes. Observations indicate that sometimes dust geometry is to blame. A dust cloud obscures the central lamp. However, in some cases, the key is accretion starvation or a surge. The inflow rate drops, the thin disk transitions to a hot, rarefied mode, and the photons ionizing the broadline region disappear. Then the process reverses. By analyzing the delays in the responsive gas lines to continuum variability, researchers reconstruct the sizes and structure of regions, and by their rates and colors, the physics of transitions between states, which links galactic nuclei to microquasars. These inverters offer a rare opportunity to test how the entire machine reconfigures from the horizon to hundreds of light years. Fact 40. Sagittarius A star, the supermassive black hole closest to us, has become a testing ground for verifying general relativity in a strong field within human timescales. The star S2, completing an elliptical orbit in less than 2 decades, accelerates to several thousand kilometers per second at its pericenter and dives to distances where relativistic corrections are noticeable. During its pericenter passage, gravitational redshift of its spectral lines was recorded, and, years later, preliminary signs of relativistic pericenter precession. The orbit's ellipse rotates by a tiny but measurable angle per orbit. Collectively, these effects align with the predictions of the Kerr metric for the relatively calm black hole at the center of the Milky Way. Next in line are even closer stars and hot gas patches whose rapid orbits will allow for recording the space-time chronicle literally minute by minute, testing the geometry near the horizon with unprecedented accuracy. Fact 41. In classical general relativity, the area of a black hole's event horizon does not decrease. This is the second law of black hole mechanics by Hawking-Bekenstein. When two objects merge, the sum of their areas must increase. Gravitational waves carry away energy, but do not allow for cheating and reducing the horizon's entropy. This statement is verifiable. From the initial phase of a gravitational wave signal, the masses and spins of the initial pair are estimated, and their horizon areas are calculated. Then, from the post-merger ring down, the parameters of the final hole and its area are reconstructed. The first events, like the historic GW 150914, showed agreement with the law within error margins. The area increased. This is not only a test of geometry, but also of thermodynamics in a strong field, a kind of cosmic version of the second law. We can add that if a naked singularity were born somewhere, the law would be violated. So such checks indirectly support the cosmic censorship hypothesis. Singularities hide behind the horizon. Fact 42. The interior of a rotating black hole, according to Kerr's solution, is richly structured. Besides an outer horizon, there is an inner one, the so-called Cauchy horizon. In an ideal mathematical picture, space-time continues beyond it, leading to exotic regions with altered causality. However, physics suggests instability. The slightest disturbances, such as falling dust or light, are amplified, and the energy at the inner horizon formally surges, a phenomenon termed mass inflation. A realistic black hole likely lacks a smooth continuation. The inner horizon transforms into a region of a destructive curvature cascade. It is important to remember that all of this is hidden from an external observer. No signal from within can cross the outer horizon, and the described effects remain purely theoretical. Nevertheless, they are significant. The predictability of the theory, global hyperbolicity, depends on the stability of the Cauchy horizon, and discussions about firewalls, quantum corrections, and holography often revolve around these inner boundaries. Fact 43. The motion of stars near a supermassive black hole is governed by a lost cone, a range of angular momenta wherein orbit will lead an object either inside the tidal disruption radius or towards the horizon. Two-body and resonant relaxation gradually mix stars into this cone, and rare victims become fuel for tidal flares. A separate topic is the Hills mechanism. If a close binary star enters the core, tidal forces tear the pair apart. The whole captures one component into a tight orbit and ejects the other as a hypervelocity star at speeds of thousands of kilometers per second. Such runaways have already been detected in the Milky Way's halo, and their trajectories point towards the galactic center. The S-star family also resides there, young, fast, on elongated orbits likely formed in the disk or delivered by dynamical processes. The sum of these phenomena is a chronicle of gravity's quiet hunt near the central monster. Fact 44. Where do pairs of black holes that sing in detectors come from? There are several channels. In isolated evolution, a massive binary star passes through a common envelope, moving closer. Low metallicity reduces stellar winds, leaving heavier cores and potentially aligning spins, resulting in mergers with relatively aligned rotation directions. Another path is dynamic. In globular and nuclear clusters, gravitational encounters bring singles into pairs, ejecting lighter competitors. Here, spins are often chaotic. Hierarchical mergers are possible, producing components in a mass range forbidden for single stars. The third candidate is active galactic nuclei disks. Migration in gas, pressure traps, orbit alignment in the disk plane, mass growth through accretion. Observational fingerprints are the distributions of eccentricities, masses, redshifts, and, most importantly, angles between spins and orbit, by which event statistics gradually distinguish the contribution of each scenario. Fact 45th. To explain quasars in the early universe, seeds of supermassive black holes are needed, which manage to grow within a few 100 million years. One scenario is direct collapse. In halos with atomic cooling temperature, where molecular hydrogen formation is suppressed, for example by a strong Lyman-Werner background, gas does not fragment into stars but falls monolithically, birthing a supermassive star of 10·4 to 10·5 solar masses, and then a quasi-star with a black heart. Another is the remnants of the first stars, population 3, with masses around hundreds of suns, which, under favorable conditions, grow super-Eddingtonially and through mergers. There is also a path through a runway of collisions in super-dense young clusters, gathering intermediate masses. Checks are ongoing on several fronts: the luminosity and lines of the most distant quasars, the statistics of their numbers, signs of active nuclei in galaxies at large redshifts, and indirect traces of feedback affecting the ionization and metallization of the early intergalactic medium. Fact 46th. The two most discussed black holes, M87 star and Sagittarius A star, share a similar shadow but operate at different paces. The characteristic gravity time, Tg equals gm/c³, for SGRA is about 20 seconds, and an orbit on the inner stable circle lasts tens of Tg, meaning minutes. For M87 star, Tg is hours, and an orbit takes weeks. Consequently, long interferometric exposures of the event horizon average the dynamics around M87 but blur the rapid changes at SGRA. Hotspots and flows manage to reconfigure during the observation time. An additional complexity at the galactic center is interstellar scattering. Electrons along the line of sight blur the radio image, and this effect must be compensated for. Phases of closure and polarization help to save contrast. They revealed that the fields of both objects are ordered and the flow is rotating, but at SGRA, photons dance faster than we learn to capture their chronicle. Fact 47. In some seemingly calm galactic nuclei, quasi-periodic eruptions have been detected in soft X-rays. These bursts repeat with intervals of hours or days, grow within minutes, and fade just as quickly, increasing luminosity by several times, sometimes tens of times. The accompanying radio emission is usually weak, suggesting a secondary role for the jet, with the inner disk and corona being the primary actors. The masses of the central black holes in these systems are estimated to be between 100,000 and 1 million solar masses, which aligns with characteristic light scales consistent with observed delays. Competing interpretations exist: partial tidal shredding of a star on an eccentric orbit, local thermal instabilities within the disk, or periodic gas inflow from a wind. The initial period stability is surprising, but then begins to drift, as if the orbit or feeding mode is slowly changing. There is no consensus, but QPEs themselves have provided a new window into the physics of thin accretion layers around small, supermassive black holes. Fact 48. X-ray reverberation, which manifests as second-to-hour echoes between the corona and the disk, has become a tool for measuring the geometry of the region near the event horizon. In the lamppost configuration, a compact corona above the pole shines downwards. Some of these photons reflect off the disk, creating an iron line and a hump in the tens of keV range. Changes in the primary continuum appear first, followed by reflected signals with a delay of around a few gm/c³, which translates to milliseconds in microquasars and minutes to hours in active galactic nuclei. These time lags, along with the line shapes, allow for the estimation of the corona's height, often less than 10 gravitational radii. the disk's ionization state, and even the detection of light bending predicted by general relativity. Scaling the lags with mass provides an independent estimate of the black hole's mass, complementing the classic optical reverb mapping of broad lines. This collectively results in a rare achievement, a form of geodesic tomography of spacetime based on light travel delays. Fact 49. The metallicity of a star's progenitor significantly influences the mass of a black hole. A star poorer in heavy elements has weaker, linearly driven winds and loses less mass before collapse, resulting in more massive cores and black holes. In close, rapidly rotating binaries, chemically homogeneous evolution is possible. Mixing prevents the star from expanding, it avoids destructive phases, and the pair maintains its closeness, a basis for the future merger of two massive holes. Add a fallback during a supernova, and you get weak birth kicks that increase the chance of the system surviving. Gravitational wave statistics hint that more massive events are more often found at large redshifts, where average metallicity is lower, a neat touch to the picture of cosmic depletion in early epochs. However, the causal link is not directly confirmed, so conclusions are drawn cautiously by fitting stellar models, binary dynamics, and observed demographics. 50 fact. Binary supermassive black holes are an expected outcome of galaxy mergers, but capturing them at sub-parsec distances is difficult. At kiloparsec distances, two active nuclei can be directly observed. Closer in, indirect markers are sought. Quasar light periodicity, double or drifting broad line peaks, and S-shaped jet bends. Many such signals have turned out to be rare noise, cloud kinematics, or disk effects, leading the community to be strict with candidates. Theory long debated the final parsec. How would a pair shed orbital momentum when surrounding stars are already sheared out? Solutions include three-dimensional, non-spherical, gas disks with torques, and massive perturbers. The nanohertz gravitational wave background, detected via pulsar timing, is precisely expected from a zoo of such pairs. It won't pinpoint a single culprit, but will confirm that for billions of years, the universe has been filled with a chorus of slow, close dances of black hearts. Fact 51. X-ray polarimetry has become a new key to understanding the geometry of regions near the event horizon. While spectra and time delays tell us what and when, the orientation of the polarization vector reveals where and how the fields and rays are directed. Modern instruments have, for the first time, measured the fraction and angle of polarization in black hole binary systems and active galactic nuclei. In the hard state, moderate but stable polarization is detected. When transitioning to the soft state, the angle changes, as if the corona moves closer to the disk or, conversely, stretches into the base of a jet. The reflected component, associated with the iron line, is polarized differently, allowing the contributions of the corona and the disk to be distinguished by their signatures. By correlating polarization phase rotations with quasi-periodic oscillations, researchers reconstruct the height of the photon source and the degree of trajectory bending in general relativity. This is a rare instance where a three-dimensional picture of directly unobservable phenomena can be extracted from a single light curve. Fact 52. The ideal test for general relativity is a pulsar in a tight orbit around Sagittarius A star. Its pulses are like ticks of an atomic clock, sensitive to time dilation, precession, and the Shapiro effect. But radio waves in the galactic center scatter off turbulent plasma, blurring the rapid rhythm. In 2013, a magnetar, a rare pulsar relative, was found near SGR A star, and its signals helped measure the degree of scattering and the magnetic environment along the line of sight. It turned out the fog was less than feared, meaning the chance of finding regular pulsars remains. If a millisecond synchronized beacon on an orbit with a period of months to years can be caught, its timing will yield mass with unparalleled precision, measure spin, and even the central object's quadrupole moment, a direct test of the Kerr metric's hairlessness. For now, this is a task for deep surveys at frequencies where scattering is weaker, and for patience. The search is like fishing in a noisy river, but the catch is worth the effort. Fact 53. Black holes and dark matter are encountered in theory at the event horizon and in the centers of galaxies. If a supermassive black hole grew slowly at the center of an already existing halo, calculations predict a spike, a sharp concentration of dark matter around it, which could amplify signals of possible annihilation. In a real galaxy, stellar bars, tidal forces, and mergers can blur this profile, so there is no direct confirmation. Gamma-ray observations of the Milky Way's center provide conflicting hints and impose strict limits. On the other hand, dark matter could influence the growth of black holes by supplying additional mass to the core and altering the dynamics of the star cluster. This effect is subtle and model-dependent. It is correct to say that the interaction of black holes with dark matter is an active area where observational scissors are narrowing the parameter space, but a final picture is not yet available. Any claims of detecting spikes require caution and independent verification by different telescopes and methods. 54th fact. Flares from black hole binary systems trace a characteristic hysteresis loop on the hardness intensity diagram. Initially, from a quiet state, the object gains brightness in the hard spectrum, dominated by a hot corona and a stable, compact jet. Upon reaching a threshold, the system transitions to a soft state. The thin disk heats up, the hard component weakens, the jet dies down, and sometimes single plasma bullets are ejected along the way. During the brightness decline, the reverse transition occurs at a different luminosity, hence the loop. The physics is asymmetric. Causes are attributed to the evaporation-condensation of the inner disk, changes in corona height, and magnetic flux. This cycle lasts weeks to months, but scales to larger masses. In active galactic nuclei, similar transitions stretch over years to decades and explain the changing appearance of quasars. Hysteresis is not just a pretty picture, but a map of regimes, linking the disk, corona, and jet into a single machine. Fact 55th. Water can become a laser for an astrophysicist. In the nuclei of some galaxies, H2O molecules in the dense, warm layers of the disk produce a megamaser, powerful microwave radiation at 22 GHz. In NGC 4258, such lights are aligned along an almost perfect Keplerian disk, allowing the mass of the central black hole and the geometric distance to be measured with benchmark accuracy, by frequency shift, velocity, by angular position, radii, and by their change, acceleration. This results in pure Newtonian mechanics near the horizon, without complex assumptions about luminosity. Such systems are rare but invaluable. They calibrate the cosmic distance scale, refine the Hubble constant, and provide scales for intermediate mass black holes. Where dust makes optics powerless, radiomasers map the disk with billionths of a second precision, showing how gas orbits within the last tens of thousands of gravitational radii before the point of no return. Fact 56. Radio galaxies with an X-shaped morphology are visual records of abrupt changes in jet direction. The images show two pairs of lobes, one active and narrow, piercing the intergalactic gas, and the other pale wings stretched perpendicularly. The spectral age of these wings is usually greater, indicating their electrons have aged. This suggests the outflow once went in that direction, but the axis then reoriented. Several mechanisms explain this. A rapid flip of the supermassive black hole spin after merging with another can cause the jets to change direction almost immediately. A slower process is the alignment of the inner disk with the spin plane, following Bardeen-Pedersen principles. The jet axis creeps, leaving curved trails. There's also a backflow version. Plasma from the main lobes returns and spreads sideways, drawing the wings. Low-frequency surveys like LOFAR are finding more such relics, and their symmetry and cooling times allow estimation of how many millions of years the nucleus experienced switching, briefly revealing the history of mergers and turns of the central monster. Fact 57. Narrow-line Seyfert-1 galaxies, NLS-1, are compact analogs of quasars. Their black holes have masses on the order of millions to tens of millions of solar masses and high fractions of the Eddington luminosity. Their spectra are rich in Fe2, the Hb line width is small, and there is often a soft excess in X-rays. For a long time, it was believed that powerful relativistic jets were the domain of massive nuclei. However, with the launch of gamma-ray observatories, jetted NLS-1 have been identified. Some exhibit variability and high-energy flares like many blazars. This implies that the thin disk can transition to a slim state under super-Eddington accretion, where radiation is partially trapped and carried away by the outflow, and magnetic fields gather the jet even at low masses. There are caveats. Mass estimates using line widths for such objects may be underestimated due to geometry and radiation pressure. But the overall conclusion remains. Jet engines are launched under a wider range of conditions than previous unification schemes assumed. Fact 58. Black holes are at the forefront of multi-wavelength astronomy and neutrino physics. When a blazar, which is a jet directed almost towards us, flares up, not only photons but also high-energy neutrinos can be born within its core. In one of the prominent cases, a high-energy neutrino from an Antarctic detector coincided in the sky and in time with an active blazar, and ground-based gamma-ray telescopes registered accompanying flare. This interpretation supports hadronic scenarios. Protons in the jet collide with photons, producing pions, whose decays yield neutrinos and gamma rays. However, the statistics are borderline, and not all such associations are confirmed due to significant background and red noise variability. Nevertheless, the very possibility links black holes to cosmic ray factories up to peta-electron volts and beyond. Radio galaxies like the nearby Centaurus A and blazars with powerful jets remain key suspects, and each multi-channel outburst is a test for models of particle acceleration near the horizon and in jets. Fact 59. Polarization in the submillimeter and millimeter ranges has served as a compass for mapping magnetic fields at the event horizon. For M87 star, interferometry revealed not just a shadow, but a map of polarization vectors, which are aligned like hoops and spokes, suggesting a strong toroidal field holding the base of the jet. At Sagittarius A star, the measured Faraday rotation measure, the rotation of the polarization plane by plasma, is enormous, indicating a hot, ionized environment near the hole and setting an upper limit on the accretion rate. If too much gas were falling in, depolarization would eat the signal. Estimates suggest that the characteristic inflow to the galactic center today is extremely modest, orders of magnitude lower than solar mass per million years, explaining its hungry state and infrequent flares. Combining polarization maps with GRMHD models strengthens the conclusion that the magnetic flux at the horizon is large, and the disks often operate in a magnetically arrested state, where the jet is powered by the black hole's rotational energy. Fact 60. The search for binary supermassive black holes often relies on periodicity in quasar light, but nature is tricky. Accretion red noise can easily masquerade as cycles. Nevertheless, several systems hold attention. In one of them, the optical light curve for years showed an almost sinusoidal pattern with a period of several years, as if the pair's orbit was altering Doppler boosting. Another, a famous blazar with a century-long record of outbursts, exhibits quasi-periodic double peaks interpreted as impacts of a secondary companion onto the primary's disk during pericenter passage on a highly inclined orbit. Spectra sometimes reveal split broad line peaks hinting at two moving sources, and parsec-scale radio jets bend in an S shape as if the axis is precessing. Each of these clues alone is unreliable, but together with the nanohertz gravitational wave background, they paint a consistent picture. Binary nuclei exist, but catching them red-handed before the final merger is difficult. Fact 61. The Eddington limit is the light ceiling for accretion. When the radiation pressure, scattering off electrons, balances gravity, the gas flow stops falling freely. The formula gives a characteristic luminosity of L-ed approximately 1.3 times 10 to the 38 m over m sol ergs per sec for plasma with Thomson scattering. But nature is tricky. Firstly, if radiation escapes unevenly in a narrow solid angle, beaming, the local flux can exceed the average limit without the disk exploding. Secondly, at high accretion rates, a slim disk is activated. A photon trap and advection carry energy inward faster than it can escape outward, and a geometrically thickened disk shields itself. The result is that super Eddington episodes are real. Ultraluminous X-ray sources and some Seyfert galaxies are estimated to live this way, shedding excess momentum with winds. The limit remains a guideline, not a hard ceiling. It is circumvented by geometry, transport, and the magnetic architecture of the flow. 60-second fact. The merger of black holes leaves not only a chirp and decaying overtones in the fabric of spacetime, but also a faint, persistent trace, the effect of gravitational memory. As waves carry away momentum, observers at infinity experience a one-time metric jump. Two test masses, which were shaking in sync, are displaced by a tiny amount after the front passes. There are linear and nonlinear Christodoulou memory. Both are extremely small for individual events in the LIGO range, but the cumulative contribution of billions of distant mergers forms a slow, creeping displacement to which millisecond pulsar timing is particularly sensitive. Pulsar timing is precisely looking for such correlated trends in the sky. For ground-based detectors, memory remains a challenge. It requires rare, very powerful, and close events, or clever processing of a large stack of signals to isolate the barely noticeable step-like tail after the ringing of the newborn whole. Fact 63rd. A black hole's magnetosphere is not empty space, but a rotating electromagnetic mechanism. Rapid spin and space-time curvature induce electric fields, and a weak plasma is sufficient to close currents and transition into a nearly inertialess, force-free state. But where does the plasma originate if the horizon itself is cold? It is generated by electron-positron pair cascades. Curvature gamma radiation from accelerated particles and photon-photon interactions with the disk's ultraviolet X-ray radiation create pairs, filling gaps, regions where the field cannot be shielded in time. Within the magnetosphere, light surfaces exist where core rotation would reach the speed of light. Through these, open field lines escape, drawing out a relativistic outflow, the basis of a jet. Currents close through the disk and corona, potential differences reach colossal values, and the Blandford's-Nyack mechanism extracts rotational energy, turning the black hole into a cosmic generator powering the jet and winds. 64th fact. Radio galaxies are divided into two Fanaroff-Riley families. Type FRI are edge-dark. Jets lose collimation along the way, breaking up into clumps and cocoons, with brightness fading towards the ends. This typically occurs with moderate powers and a denser environment, where the outflow captures surrounding gas and slows down. Type FR2 are edge-bright. Narrow, straight jets impact intergalactic gas, forming hotspots at the ends of the lobes. These have higher powers and a cleaner path. The dividing line is approximate and shifts with mass and environment, but it hints at the underlying physics. Different feeding and magnetic flux modes at the horizon, different surrounding density, and the speed of entrainment. This is reflected in the spectra of the nuclei as LRG/HRG, low and high excitation radio galaxies, resembling the hard and soft states of microquasars. This creates a scalable picture, the same disk corona jet engine, but on megaparsec scales and with different environmental aerodynamics. Fact 65th. If the Sun were miraculously replaced by a black hole of the same mass, the planets would not fall into the abyss. Their orbits and periods would remain the same. Gravity at a distance is the same. Everything else would change. After more than 8 minutes, Earth would plunge into night, photosynthesis would stop, and the climate would begin to cool down. Within days to weeks, the average temperature would drop significantly below zero. Oceans would begin to freeze over from the top, but warm depths and geothermal flux, 0.1 W per meter squared, would keep liquid water under the ice shell for a long time. Volcanism and tidal heating, minimal for us, would become local refuges. The solar wind would disappear, restructuring space weather, and auroras would become rarer. Neither a vacuum cleaner nor an instant collapse of celestial mechanics would happen. The main lamp in the sky would simply die, and an invisible, relatively quiet object would remain at the center of the solar system, which under normal conditions receives almost no fuel for accretion and therefore does not glow. 66th fact. The center of the galaxy holds records of recent flares from Sagittarius A star in the form of light echoes on molecular clouds. Tens to hundreds years ago, the supermassive black hole was more actively fueled by gas. Its hard radiation struck nearby clouds, knocking out a fluorescent line from iron at about 6.4 keV. Now, long after the flare has passed, we observe the illumination seemingly running across the cloud. Bright spots appear and disappear over the years like a spotlight gliding over an uneven surface. Such a shift cannot be explained by internal processes within the cloud itself. It reflects the fleeting past activity of the core. Based on the rate and amplitude of the echoes, scientists estimate the power of the past flare and the precise location of the cloud on a three-dimensional map of the center. This creates a chronicle. Today, SGR-A star is quiet, but a century ago, it likely flared up briefly as a mini-active galactic nucleus. Fact 67. In 2020, the Nobel Prize in Physics was awarded for work on black holes, encompassing both theory and observation. Roger Penrose received the award for his rigorous demonstration that black hole formation is an inevitable consequence of general relativity under sufficiently general conditions of collapse. Reinhard Genzel and Andrea Ghez were recognized for their discovery of a supermassive compact object at the center of the Milky Way. Their research teams spent decades tracking the orbits of S-stars around Sagittarius A star, measuring their accelerations, pericenters, and precession with incredible precision. The physical essence of their finding is that the observed mass is concentrated in a volume where nothing stable other than a black hole could exist. This bridge between equations and the sky revealed how Penrose's strict mathematics and the delicate diffraction patterns from telescopes merge into a unified picture of the gravitational abyss at the very heart of our galaxy. Fact 68. Even the most modest galaxies can hide black holes. In dwarf systems, active nuclei have been found with estimated masses of hundreds of thousands of suns and below. An example includes galaxies without a bright bulge, where central variability and narrow lines are still visible, and sometimes water megamasers, indicating a compact Keplerian disk. Such micronuclei are important as direct clues to the origin of supermassive monsters. If small holes are found in dwarfs, it means that seeds could have been numerous and scattered throughout the young universe. Another class is wandering black holes, remnants of torn satellite galaxies or products of gravitational kicks that have moved away from centers and now roam through halos, sometimes igniting as insignificant off-center active nodes. The search for such wanderers is conducted by looking for displaced nuclei, line asymmetries, and X-ray points outside stellar centers. Fact 69th. Ultraluminous X-ray sources are points beyond galactic nuclei whose luminosity exceeds the Eddington limit for a normal star. For a long time, they were considered almost certainly intermediate mass black holes. But after years of observations, some ULXs revealed a pulsar nature. Stable pulsations were detected in their light, a signature of a rotating magnetic neutron stellar core. This means that super-Eddington fluxes are possible not only for black holes. Geometric collimation, magnetic channels, and photon traps allow neutron stars to exceed the classical limit by several times. This does not negate the existence of intermediate black hole candidates, but teaches caution. High luminosity by itself is not yet a seal of mass. Recognition requires spectra, pulsations, cyclopic lines, and the dynamics of optical donors, a whole set of signs to avoid mistaking a strong accretion regime for high gravity. Fact 70. In the demography of compact objects, mass gaps are discussed. The lower gap is between the most massive neutron stars and the least massive black holes. For a long time, black holes lighter than about 5 solar masses were not found in X-ray binaries, and it seemed there was a forbidden zone. Gravitational waves have added nuances. In one event, the secondary component fell into the range of about 2 to 3 solar masses, either a record-heavy neutron star or an unusually light hole. The upper gap is related to the pair instability evolution of massive stars. Single progenitors do not leave black holes in a specific mass range, but hierarchical mergers and clusters can tune masses directly into the forbidden corridor. As a result, these voids turn out not to be walls, but thin spots in a complex network of formation channels, where stellar statistics and physics intertwine with the dynamics of close encounters. Fact 71. Hawking's ideas about quantum evaporation are tested in laboratories not on actual gravitational holes, but on their analogs, artificial horizons. In superfluid Bose-Einstein condensates, a region is created where sound cannot escape against the current. In optical waveguides and photonic crystals, a moving boundary of the refractive index is modeled, which acts as a horizon for light. In such systems, correlated pairs of quasiparticles, acoustic or optical, are observed on both sides of the boundary, as predicted by the pair creation mechanism at the horizon. These Hawking sparks convincingly demonstrate the principle itself, but do not prove the evaporation of astrophysical holes. Gravity and space-time curvature operate there, while here an effective medium with an analog metric. It is important to distinguish. Experiments support the general idea of quantum pair creation at the horizon, but their direct translation to cosmic masses should be approached with caution. Fact 72. In discussions about the nature of compact dark objects, alongside the concept of a Kerr black hole, alternatives are considered: boson stars, gravastars, exotic configurations with fields, or even wormholes. Their common feature is the absence of a true event horizon. In such cases, light and gravitational waves might partially reflect, creating an echo after the main merger ringdown. The shadow's photograph would exhibit altered edges and contrast, and its spectra would show a different structure of reflection lines. According to interferometry data of the shadows of M87 star and SGR-A, as well as the ring-down Bell formulas for gravitational waves, the classical Kerr metric still describes the observed phenomena reasonably well. However, windows for exotic scenarios remain open, as the signals are weak, systematics are significant, and alternative models are flexible. It is correct to state, today we have no reliable deviations from the Kerr picture, but the search for echoes and subtle effects continues, as these are precisely what would distinguish a horizon from a reflective skin. Fact 73. Hotspots periodically flare up in the near-infrared range around Sagittarius A star. These are compact plasma clumps heated in the corona above the disk. Long baseline interferometry observed one such spot orbiting the black hole several times within a period comparable to tens of minutes. During this, the light's polarization vector smoothly rotated, resembling the observation of an orbit in a strong field with twisted magnetic lines. The period and amplitude align with motion at radii of just a few gravitational radii, meaning distances where relativistic effects dominate: Doppler boosting, aberration, and gravitational redshift. Such flares are low in energy and quickly fade, but they are invaluable as a stopwatch near the event horizon. Their rhythm and polarization turns allow for estimating spin, disk tilt, and magnetic field structure without waiting for rare, large accretion feasts. Fact 74th. The M87 jet is a textbook example for studying relativistic plasma aerodynamics. Across scales from tens to hundreds of thousands of gravitational radii, its transverse profile closely follows a parabolic line with gradual widening, indicating magnetic collimation and external environmental pressure. Further out, the jet becomes more conical as pressure drops and the flow proceeds inertially. Images reveal edge brightening, bright rims suggesting a velocity shear between a fast core and a slower sheath, which aids in maintaining collimation and accelerating particles. The polarization and brightness at the jet's base align with a magnetically arrested disk scenario. Substantial magnetic flux is fed to the horizon, and the black hole's rotational energy is extracted electromagnetically. Choke points along the way, recollimation shocks, produce localized flares and structure the jet on parsec scales, illustrating how microphysics at the horizon scales up into giant cosmic structures. Fact 75th. The next generation of ground-based gravitational wave observatories, featuring arms ranging from kilometers to tens of kilometers, aims for black hole spectroscopy. Their enhanced sensitivity will enable not only the confident detection of the primary ring-down after a merger, but also the capture of individual overtones. This will allow for simultaneous checks of the no-hair theorem using multiple frequencies. For cosmology, this translates to a map of mergers reaching deep into redshift, and direct standard siren distance measurements. For astrophysics, it means obtaining statistics on spins and masses, including intermediate mass black holes born in dense clusters. Concurrently, a space-based millihertz antenna will detect the in-spiral of massive pairs years before they merge, and pulsar timing will refine the background from supermassive nuclei. Although pure black hole mergers are electromagnetically dark, clues in the form of flares from disturbed gas may be found in active galactic nuclei disks. Joint observations will offer a rare opportunity to connect event horizon geometry, plasma, and galaxy growth into a single, testable narrative. Fact 76th. The cooling flow problem in galaxy clusters once promised a deluge of stars. Hot intergalactic gas at the centers was expected to cool rapidly and settle into the cores. However, observations revealed a different scenario. Star formation was modest and the gas remained hot. It was discovered that supermassive black holes act as thermostats. Their jets inflate bubbles, cavitations, within the X-ray emitting gas. The enthalpy of these bubbles, around 4 PV, compensates for radiative losses. The bubbles rise, lifting cold filaments and mixing the medium. Faint shock fronts and sound ripples, like those seen in Perseus, are visible along their paths. The cycle closes. When the gas in the center overcools, droplets condense, chaotic cold accretion, and fall towards the black hole, boosting its feeding and heating. This feedback mechanism operates over tens of millions of years, providing gentle but persistent heating that prevents clusters from experiencing a snowstorm of star formation. 77th fact. Variability is the hallmark of accretion, and for black holes, it scales. Their X-ray light curves resemble red noise. The power of fluctuations grows with longer timescales but breaks at a characteristic frequency. This break frequency systematically shifts with mass and specific accretion rate, forming a variability plane with them. Small and hungry objects flicker faster, while large and well-fed ones do so more slowly. Another signature is the RMS flux relation. The brighter the system is at a given moment, the larger the relative fluctuations, as if fluctuations are amplified on their way in. The propagating disturbances model describes this. Irregularities in viscosity and supply originate at larger radii and, drifting inwards, modulate the light from the corona and disk. In optical and ultraviolet wavelengths, delays after X-rays are often seen, the response of outer layers to heating. Sometimes the opposite occurs, with a slow optical pulse leading, suggesting excitation came from deeper within the disk. Fact 78. Flares from black holes are echoes of the disk's thermally viscous instability. In a cold state, hydrogen is predominantly neutral, opacity is low, and the disk accumulates mass. When the temperature in a ring crosses the partial ionization threshold, opacity sharply increases, amplifying heating. This activates the upper branch of the S-shaped equilibrium curve. A heating wave propagates through the disk, transitioning it to a hot, bright state for weeks to months. Then, as fuel is depleted and cooling occurs, a reverse wave extinguishes the light. X-ray irradiation of the outer layers shifts the thresholds and stretches the plateau. During deep silence, the inner disk can evaporate into a hot, rarefied outflow akin to an ADAF, and radio jets become active during transitions. The same physics, stretched over years, is discussed for active galactic nuclei as a mechanism for changing appearance. The disk accumulates mass for a long time, then spends it quickly, while the corona and winds contribute to the changing chords. Fact 79th. The cosmic X-ray background, a faint curtain in the sky peaking around tens of keV, turned out to be a roll call of billions of active nuclei, including hidden ones. To assemble its spectrum, strongly absorbing Compton-thick sources with NH columns above some 10 to the 24th centimeter-2 are needed. Their direct light is eaten away, but reflected and leaked photons accumulate power at high energies. Synthetic background models piece together the puzzle from quasar luminosity functions, absorption distributions, and their evolution with redshift, achieving agreement with the spectrum and number of identified sources. Deep Chandra and XMM surveys resolved a significant fraction of the background at soft energies, while NuSTAR brought the hard keV, highlighting the population of hidden nuclei. Through the Sultan argument, the AGN luminosity integral is linked to the total whole mass today, yielding an average radiative efficiency of tenths, a hint at considerable spins in a significant portion of the central monsters. Fact 80. The signal from merging black holes encodes physics in its form, frequency, and amplitude increase according to a law defined by the chirp mass mc equals m1 m2 to the 3/5 divided by m1 plus m2 to the 1/5, which is determined most accurately. The mass ratio, precession, and spins are read with more difficulty. Key parameters include the effective spin, chi-f, which is the weighted average projection of spins onto the orbital axis. If it is systematically positive, this suggests aligned spins and possibly isolated evolution. A chaotic distribution favors dynamical mergers. Traces of eccentricity at the time of detection are usually small, but their search is ongoing. Unusual harmonics will reveal a recent dynamical close approach. Localization in the sky improves with a network of detectors. 3 or more observatories narrow down the region to tens to hundreds of square degrees. Even without light flashes, such dark sirens can, in principle, calibrate cosmology statistically by comparing volumes with galaxy catalogs, another way to extract cosmic information from pure gravity. Fact 81. The photon ring is not the same as the thick, glowing halo seen in shadow images. The observed ring is the sum of radiation from the disk and corona blurred by turbulence and the interferometric aperture. The true photon ring itself consists of subclasses of subrings. Rays that have completed 1, 2, 3, or more orbits around the black hole contribute increasingly finer and weaker signals. Theory predicts an almost geometric dimming of brightness and an exponential compression of width from one subring to the next. Their shape and displacement are sensitive to the mass, spin, and inclination of the system. To distinguish them, very long baselines and frequencies that minimize interstellar scattering are needed, along with precise closure phases. Characteristic nulls and a comb should appear in the visibilities. Detecting subrings will transform the shadow from a beautiful picture into a precision ruler for Kerr geometry, separating the influence of plasma from pure gravity. Fact 82nd. Microlensing of quasars acts as a natural scanning needle, with stars in the lensing galaxy probing the background accretion disk. As a caustic passes over the source, different radii and sectors are amplified multiple times. By analyzing the color and temporal signature of the flash, the disk size law, R of lambda, can be reconstructed. For a Shakura-Sanyev thin disk, the expectation is R proportional to lambda to the 4/3. However, observations often reveal larger sizes and smoother temperature gradients, hinting at the role of scattering, the corona, and irradiation. Sometimes, a caustic captures a reflected component. The K-alpha iron line drifts and distorts as if from local illumination of the inner edge, serving almost as a laboratory for a relativistic line at cosmological distances. Combined with polarimetry and continuum time delays, this method offers rare access to the two-dimensional structure of the disk and corona without requiring spatial resolution. Gravity itself draws a map of the glowing film near the horizon. Fact 83rd. Not every star near a supermassive black hole experiences a bright tidal disruption. There is the Hills mass. If the hole is too heavy, its tidal radius falls inside the event horizon, and the star is swallowed without an electromagnetic spectacle. For a non-rotating hole, this threshold is around tens to hundreds of millions of solar masses for a Sun-like star. Rapid spin and a prograde orbit can raise the boundary, opening a window for disruptions of more massive objects. Conversely, in a pair of an intermediate mass hole and a white dwarf, particularly fiery events are predicted. A compact, dense star might survive a thermonuclear burst upon disruption, illuminating the gamma-ray and X-ray range. There are also partial nibbles on eccentric orbits, yielding repeated mini-bursts. The observed TDE demographic aligns well with these constraints. The most massive cores show fewer flares, and spin and geometry are the invisible directors of the finale. Fact 84th. The paradox of youth in the galactic center is how O and B-type stars could form where the black hole's tidal forces should hinder assembly. Observations of disk structures offer an answer. At some point, so much cold gas flowed into the core that a self-gravitating ring disk formed in its plane. This disk cooled, developed instability spirals, and fragmented into stars right under the nose of the event horizon. This resulted in a top-heavy initial mass spectrum, an excess of massive stars, as predicted by models of dense, irradiated environments. Traces of such a scenario are also visible in other galaxies. Maser Keplerian disks and infrared rings tens to hundreds of parsecs from their nuclei. An alternative pathway involves the infall of a compact young cluster, which, losing energy through friction, slides towards the center. During this process, some stars are tidally stretched, while others survive on elongated orbits of the S family. Both mechanisms are not mutually exclusive, and together explain why a nursery is possible at the edge of a gravitational abyss. Fact 85th. The corona of an accreting black hole is a hot tens to hundreds of keV electron-positron plasma. In this plasma, soft photons from the disk undergo multiple Compton scatterings, boosting them to a high-energy tail. Its temperature and optical depth are not arbitrary. At high compactness, defined by L equals L sigma T over RMEC cubed, electron-positron pairs begin to be produced in avalanches, increasing optical depth and cooling. This is the pair thermostat. Consequently, the spectrum forms an exponential cutoff at energies around 50 to 200 keV, which is indeed observed by hard X-ray observatories. During flares, this cutoff drifts as if the corona is rising/falling and changing its density. The geometry remains a subject of debate. A compact lamppost above the axis, the base of a jet, or a flat sandwich corona above the disk. Polarization, reverberation lags, and reflected components collectively paint a picture. The corona is compact, a few to 10 gravitational radii, rich in pairs, and likely partially involved in the magnetic energetics of the jet, connecting pair microphysics with jet macrophysics. Fact 86. The cosmic censorship hypothesis suggests that singularities, if they arise, are hidden behind the event horizon. Theoretically, it's tempting to overspin a black hole, giving it a spin exceeding the Kerr limit, or adding a charge. This would cause the horizon to disappear, exposing a naked singularity. Classic thought experiments, starting with Wald's argument, show that nature intervenes. Particles with the necessary parameters either don't reach the horizon, or, due to back reaction and radiation, disrupt the attempt. Similar conclusions come from calculations considering gravitational self-interaction and superradiance. The system self-protects by preventing trajectories that lead to a parameter A*1. In astrophysics, magnetic and photonic feedback from accretion is also added. Disks and corona remove angular momentum more effectively than they increase spin. Observations also don't reveal naked objects. Images of the shadow, ring-down spectra after mergers, and the absence of stable optical/X-ray surfaces are consistent with the existence of a horizon, although censorship hasn't received perfect proof yet. 87th fact. A star's tidal disruption is not an instantaneous splash into a disk, but a drama of shocks and orbital mechanics. Torn streams of gas first return to Paris center along elongated ellipses. Due to GR precession, their apsides are shifted, and head-on encounters create internal collisions, stream-stream shocks. If precession is large, circularization is fast, and X-rays flare up immediately. If small, the gas oscillates for a long time on extended orbits, releasing energy further from the horizon. Then optical UV light and powerful winds dominate. The spin of the hole and the orbital tilt determine the geometry, including possible dissipative nodes far from the center. Helium and nitrogen lines, including bow-shock fluorescence and broad asymmetric profiles, report on heating locations, while radio sometimes indicates a jetted regime. Warm dust provides an IR echo, mapping the three-dimensional scene. Collectively, TDEs are a laboratory not only for gravity, but also for nonlinear gas dynamic circularization in a strong field. Fact 88. A thin disk does not exhibit Newtonian viscosity. Instead, it is driven by the Balbus-Hawley magneto-rotational instability. A weak magnetic field in a differentially rotating gas causes adjacent rings to become spring-connected. The inner ring pulls the outer one forward, losing negative angular momentum and falling inward. The outer ring slows down, carrying the moment away. Subsequently, a turbulent cascade is activated, and the transport of matter in the middle layer is more conveniently described by the parameter alpha, representing effective stress relative to pressure. However, alpha is not universal. Its saturation depends on the field's topology, particularly on the presence of a net vertical flux. With a large magnetic flux, the disk enters the MAD, magnetically arrested disk, where accretion is stalled by the field at the horizon, and the jet is amplified. With a small flux in the sane, standard, and active regime, the jets are weaker and the corona is more tenuous. GRM-HD simulations with light transport reproduce observed spectra, polarization, and variability, suggesting that powerful radio galaxies and blazars indeed operate with disks possessing a large magnetic flux, acting as batteries powering the Blandford-Zeineck mechanism. Fact 89th. How to distinguish a black hole from a pseudo-hole with a solid surface. If an object lacks a horizon, infalling matter should decelerate and heat the surface, emitting thermal radiation. This is particularly noticeable during quiet phases when the X-ray corona fades. Observations indicate that, at rest, black hole X-ray binaries are orders of magnitude dimmer than neutron stars with comparable accretion rates, a direct hint of energy slipping beyond the horizon without thermal rebound. Additional tests come from the absence of stable surface lines/flares like thermonuclear bursts and from shadow maps. The contrast in size match the gravitational shadow, not a glowing crust. In gravitational waves, echoes, repeated post-merger signals from a supposedly reflective shell, have been sought. No stable signals have been found, though limits are not yet absolute. The collective evidence is substantial, but honestly, these are empirical negative proofs. The final verdict awaits increasingly precise shadow maps, polarimetry, and ring-down spectroscopy. Fact 90 states that not every massive star dies in a spectacular explosion. It is likely that some fall quietly, a failed supernova. The core collapses, the shockwave is weak, the envelope partially falls back, and a black hole is born with a minimal kick. Indirect evidence includes red supergiants that have disappeared almost without a trace. Faint transient bursts with signs of brief envelope inflation followed by silence. Demographic data of binaries where massive components are found in close orbits without clear signs of strong impact. Metallicity and rotation regulate the chances. Metal-poor stars lose less mass through stellar wind and more often retain heavy cores, while rapid spin and binary interaction can lead the system to a common envelope phase and accelerate the approach of future black holes. The natal kicks in such collapses are smaller than those of neutron stars, which helps pairs survive until merger. The picture is assembled from scattered threads: disappearing giants, quiet transients, statistics of gravitational wave marriages, and tells about another pathway for the birth of dark gravitational hearts. Fact 91. The most powerful cosmic bursts, gamma-ray bursts, GRBs, are often linked to black holes as their engines. Long GRBs last more than 2 seconds and, according to the current model, are born from the collapse of a rapidly rotating massive star. Its core collapses into a black hole, forming a hot accretion disk around it, and magnetic fields launch a narrow relativistic jet, the Blandford-Zeineck mechanism and relatives. Short GRBs lasting less than 2 seconds are likely the result of neutron-star mergers or a neutron star merging with a black hole. Milliseconds after contact, a compact hole with a disk and outflows also forms. Isotropically equivalent energies are estimated to reach 10 to the 51 to 10 to the 54 ergs. After the gamma-ray spike, afterglow follows, from the radio to X-ray range. Shock waves in the interstellar medium produce synchrotron radiation, and a jet break in the light curve indicates a narrow collimation angle. In short bursts, a kilonova is often seen, an optical infrared glow from the decay of R-process elements in the ejected material. Fact 92. Another matchmaker for stellar mass black holes is the dynamics of multiple systems. In hierarchical triples, the Kozai-Lidov mechanism causes the inner orbit to pump up its eccentricity when the outer one is inclined. The pericenter shrinks, and gravitational radiation drives the pair to merge within the age of the universe. This pathway naturally yields mergers with residual eccentricity at high frequencies and chaotic spin orientations, unlike the family-isolated evolution, where spins tend to be aligned. A similar effect also operates in nuclear clusters around a supermassive black hole. It acts as a helper, pushing binary black holes towards a merger through secular resonances. Observationally, this is sought by low values of the effective spin, chi-f, and by subtle harmonics in the gravitational wave signal that are sensitive to eccentricity. The picture emerges. Several channels coexist, and the statistics of events gradually reveal their proportions. Fact 93rd. Astrometry has enabled a quiet hunt for nearby black holes. If an unseen companion pulls a star in a small ellipse across the sky, highly precise position measurements will detect this waltz. Unlike classical X-ray binaries where accretion reveals the object, here the companion may consume very little and remain invisible. Combining astrometry, radial velocities, and photometry yields the mass of the dark body and rules out a bright companion. Such systems are important for two reasons. Firstly, they calibrate demographics. How many stellar mass black holes are in the Sun's vicinity and what are their mass and orbit distributions? Secondly, they show natal kicks. From spatial velocities and orbital tilts, one can indirectly judge if the collapse was quiet or accompanied by an asymmetric explosion. This method complements microlensing and X-ray observations, filling the gap between the galaxy's loud and silent black holes. Fact 94th. Black holes indirectly participate in the cosmological distance ladder. The brightness of quasars, which are lamps powered by accretion onto supermassive holes, makes them convenient background beacons for gravitational lensing by galaxies. If there are multiple images, the source's variability arrives in them with different delays. The path and gravopotential differ. By measuring the time delays and constructing a lens model, the geometric distance and an estimate of the Hubble constant are obtained. This is the time delay method. It is sensitive to the mass along the line of sight and to stellar microlenses, which, incidentally, comb the quasar's accretion disk, providing information about its size and temperature profile. This results in a rare alliance, a black hole acting as a lantern to measure the scale of the universe and microlenses serving as a free zoom. Although systematics are significant and require careful calibration, the method has already become an independent cosmological test alongside supernovae and the cosmic microwave background. 95th fact. The era of black holes is the distant future of the universe, when stars will go out and galaxies will drift apart. It is estimated that stellar mass black holes evaporate through Hawking radiation over timescales of order 10 to the 66th to 10 to the 68 years, and supermassive ones over fantastic 10 to the 99 to 10 to the 101 years and more. The lower the mass, the lower the radiation temperature. As long as the cosmic microwave background is hotter than the hole's temperature, evaporation is suppressed. Only when the background cools will slow shrinkage begin. The final stages of evaporation of small objects will, according to theory, be accompanied by a rapid increase in power and the emission of high-energy particles. But the details remain a subject of debate due to unknown quantum gravity. A completely different end is also possible if dark energy changes or proves to be dynamic. It is correct to say that, with current understanding, black holes are the most long-lived structures in the universe, and its last light will likely be born in their final quantum whispers. Fact 96th. Theory predicts that stars near a supermassive black hole should form a cosmic anthill, a steep density concentration towards the center. In the simplest case of equal masses, this is the famous Bach-Hall-Wolff cusp. The spatial density of stars increases approximately as r to the -7/4. Real nuclei are multi-component, and heavy remnants, black holes and neutron stars, due to mass segregation, sink deeper, forming an even steeper dark cusp, while light giants and dwarfs distribute more shallowly. Observations of the Milky Way's center subtly contradict the textbook. Red giants show a shortage near SGR star, as if their envelopes were cleared by collisions and tides, and the true cusp is hidden in invisible remnants. Indirect evidence, transient flares, the population of X-ray sources, and hypervelocity stars aligns with the dark core idea. The careful conclusion is, the theoretical cusp is likely there, but its bright pins have been broken off by evolution, leaving a gravitational, not a photonic signature. Fact 97th. Disks of active nuclei are not only feeders but also matchmakers for stellar mass black holes. Within dense viscous gas, single black holes are captured into the plane, lose energy through friction, form pairs, and migrate to pressure zones, traps where encounters are unavoidable. Gas tori align orbits and spins with the normal to the disk, increasing the chance for a high effective spin, chi-f greater than 0, and merger on cosmologically short timescales. Before contact, the surrounding gas can provide faint electromagnetic illumination, quasi-periodic oscillations, and after, a afterglow occurs. The kicked newborn hole breaking through the disk excites shock waves and temporarily increases accretion. Detections are still debated. Signals are small and easily confused with the noisy variability of quasars. But the channel itself is physical and predictable. It naturally produces mergers at Z1 to 2, allows for hierarchical repeats, and potentially connects gravitational waves with rare, faint optical X-ray flares. Fact 98. Gravitational waves, much like light, can be lensed by masses along their path. In a strong lensing scenario, the same chirp signal would arrive as multiple copies with delays ranging from seconds to days. For detectors, this would mean recurring events with identical masses and waveforms but with different amplitudes. On smaller scales, stars and black holes within the lensing galaxy microlens the signal, causing the amplitude to become frequency-dependent, with interference fringes appearing in the spectrum. Such effects are not mere theoretical novelties, but expected rarities. The universe at high redshifts is rich in lenses. Searches are conducted through merger catalogs. Matching parameters and characteristic modulations would provide a lens passport and enable precise cosmological measurements. While no definitive examples exist yet, the established limits already probe interesting regions. Should lensing prove effective, we will gain another tomographic tool. The same black hole mergers will serve as beacons for mass maps along the line of sight, from galaxies to their star clusters. 99th fact. Black holes serve as a testing ground for ideas of holography and field gravity dualities. In several rigorous models, such as anti-de Sitter space, the dynamics of a black hole are equivalent to the thermal evolution of a quantum field theory without gravity on its boundary. The horizon's entropy corresponds to the number of microstates. The ringdown after a merger relates to the poles of correlation functions, and flows at the horizon are mapped to fluid dynamics equations, fluid gravity correspondence. The famous viscosity bound N over S equals H over 4 pi kb, derived in such theories, is surprisingly close to estimates for strongly interacting quark-gluon plasma in accelerators. All of this is not about specific quasars in the sky, but about principles, how quantum disorder is encoded by the horizon's area, and how information is processed into thermodynamics. An indirect but important contribution to astrophysics is that the thermodynamic laws of black holes and statistical physics converge into a single, mathematically rigid picture, a benchmark against which both cosmic observations and laboratory analogs are calibrated. 100th fact. Isolated, wandering black holes in the interstellar medium are nearly invisible. Without a donor star and a dense cloud, they feed via Bondi-Hoyle accretion, a rare process involving gas, dust at speeds of tens of kilometers per second. Typical accretion rates for masses around 10 solar masses and densities of approximately 1 particle per cubic centimeter are minuscule. Furthermore, the radiative efficiency in a hot, rarefied flow is low, as a significant portion of energy is carried inward by advection before it can become light. Consequently, the expected luminosity is fractions of a millionth of the sun's, often appearing as faint radio or hard X-ray whispers. Therefore, they are sought through other means, by stellar microlensing, by astrometric wobbles of neighbors, and by rare, brighter episodes when encountering dense clouds. Future wide-field radio and X-ray surveys, combined with precise astrometry, are expected to systematically comb out such wanderers. This closes the loop. From dazzling quasars to silent loners, the entire life of black holes is read through gravity, with light being merely a common, though not obligatory, sign of their presence.